So, great. Well, we're careening towards graduation for many of you. It's fantastic. Maybe just take 2 seconds to see where we are. Well, we've come a long way so far, and so we're in the part that's after spring break. There are only 2 more weeks in class, and so that's where we are right now. So we spent the first part of the class talking about physical hydrology, the behavior of multiphase fluids, Darcy's law, relative permeabilities, capillary pressures versus saturation curves. So you can get the picture of this chimney that exists in the subsurface, the initial distribution of the source, the contaminant that's stuck there by capillary forces. We talked about how it might dissolve and be carried by advection and be redistributed by dispersion as it goes down gradient towards a compliance location, such as Long Street for Yucca Mountain that you'd seen before, and around Smithville, which we've been messing around with. We realized that not all solutes are conservative, like salt ions, and sodium and chloride and bromine are conservative, but many dissolved solvents are not, and they can be both retarded in how quickly they go down gradient and attenuated in the magnitude of the concentration as they go down gradient. And also, in addition to everything that's happening below the groundwater table, in the vadose zone, where many of these things are trapped, we have to understand the processes by which they are removed. And I guess we convinced ourselves that rainfall washing down through them is a big mechanism by which they get removed. So that's where we are. We've covered all kind of the transport processes that we needed to. So the last couple of things we need to deal with are here, 6.1, where we are today, and also how you convert standing on a field, in a field, into something that looks like these assignments that has a stratigraphy and a distribution of contaminants in the subsurface, or where the plume looks, like the Borden results that we looked at. So the 2 things we really have to cover are modeling, to be able to do more sophisticated things than we've talked about in our back-of-the-envelope calculations for advection dispersion, which we perhaps understand the physical background for, and also sampling and drilling to be able to see what the subsurface looks like. I'm just turning my pad on. Yeah, now it works. So that's where we are. And then after that, I guess there's a week free, week 11, and then the presentations are due April 7th. There is a bit of a deadline because I've got to put them online once I get them from you. And so we've never been draconian with any of the deliverable time schedules in this class, but that's a reasonably firm deadline. And then what I'll do is I'll put them online, and I guess the first one is from last year. Oh, I didn't change these. What are how many do we have this year? Can you remember? I can't. Do we have 5 groups, 4 groups? Doesn't matter. So this is left over. I didn't change this from last year. So in 2025, we'd have had 1 remnant one from 24, and actually 3 remnant ones from 24, and we had 3 groups doing containment, electrolytic methods, and in situ washing. We have a bigger class this year, so I think we at least have 4. What size is the groups? Are they 3 or 4 people? 4. So it's probably 5. We're probably doing 5 because we have roughly 20 in the class. Okay, so this is kind of a hardish deadline, and then you'll go online on these dates, and these will be revealed to you to be able to look at your colleagues and what they made of their individual, and what you made of your individual presentations. So that's where we are in the final part of the class. So the 2 things to discuss are mathematical modeling and site characterization. So today I didn't want to do that. Or perhaps I did want to do it, but not yet. Right, so here. So Won't recap stuff from last time because it's too long ago to be able to remember it. But we'll talk about modeling. So if you end up working in this area and work in a consulting office, almost certainly you'll end up using the software that is present in the office and to do modeling of flow, much more sophisticated than the stuff that we've talked about in the class. And so what I might do is introduce it with a kind of simple example, and then also do a simple exposition of how we can do it, again with an example to show how that works. And so don't want to do that, don't want to do that. So I took this from an article quite a long time ago. It's in New Jersey. Hey. There you go, I believe. And it's a landfill. And so I think the story is that probably from the 70s, when this kind of stuff was first realized, the first half century of hydrology was physical hydrology. How do you get water out of the ground to drink? How do you make sure you don't take too much out of the ground that it's not sustainable? In other words, that you pull out the volumes in less than the quantities that would deplete the resource and take it to zero. And then since maybe the 1970s, the emphasis has been on, well, we have this resource. We definitely use groundwater, but maybe we need to protect some of it or remediate it, the stuff that's been messed up. And so contaminant hydrology maybe started in the 70s with the realization that doing things that used to be done, like, for example, at Rutgers Nice in State College, where you go up to the mall before the roads bifurcate ahead of the Nittany Mall. There's a company on the right-hand side that used to make solvents called Rutgers Nice. You'd be surprised to know that it's a EPA Superfund site. And their way of disposing of solvents was spray irrigation. So garden sprinkler, all day, every day, laying water on the ground, seeping through to groundwater, and hopefully doing something with it. So as a result of that, I think it's still a Superfund site. I'm not sure exactly what's being done with it. You're not supposed to take fish out of Spring Creek, which is the creek that runs under the road at the fireworks plant. Has anyone ever seen do you ever drive out there? Have you ever seen a car at the fireworks plant shop? Yes? It's never there. Must be a front for drugs, don't you think?
I mean, I wouldn't be surprised.
Was that why you were there?
Yeah, that's why I was there.
Yeah, fine. So the Spring Creek, which comes from Tussey Mountain, a ski hill, and ends up crossing the road at the fireworks store on the Benner Pike, is where it goes under the ground, and you're not supposed to take trout from there and eat because you can only have a certain number per year, and beyond that they're toxic, I guess, or certainly harmful. So this is a site where water is being drawn for groundwater for human consumption, found to be contaminated, so you know there's something going on here. So you take some samples. How do you, if you're standing in a field, figure out what's going on? You don't know the stratigraphy, you don't know the direction of groundwater flow, you don't know anything about the site, you don't know the size of the plume. So you drill some holes to investigate. You take water samples, perhaps you take samples from places where the plume isn't, and then you try and reconstruct what's going on. So one way to reconstruct what's going on is actually quite similar to one of your assignments. Actually, the one that I was surprised that I think you hated and didn't do well on. Oh, I hear from Matt, everyone did very well on the midterm, by the way. Congratulations. But the one you didn't do well on was the one with trying to chart the direction of groundwater flow from some wells which were not in a line. And so the idea is that if you put in some wells and try and draw some hydrologic cross sections for the water table along these two different sections, you can find out where the main pressure water table drop is. If the water table is flat, it means that the main drop must be kind of orthogonal to that. And so you could plot out the water table along a number of sections, and so that would be exactly what this is. So these are water table sections, I think, maybe along this line here. Doesn't quite go through here. And so by this, you know immediately that this is dx, right? If there happens to be a section on a different cross-section that goes like this, it means you don't have any groundwater flow. And so you might want to do a section 90 degrees to that, because then you might have a groundwater flow. So you get the orientation of the maximum gradient. And if you can project that maximum gradient onto a plot where you've sampled and you know there's a problem, then you can project. You can either look downstream or upstream, you don't know, or you can look upstream. And if you have a plot like this, you definitely know which direction is upstream and which direction is downstream. And so in this case, you know this is upstream, you look up here, you drill some more wells, and you find this was perhaps a no-brainer because this is a landfill. So it's known that it's here, and so you don't have to scratch your head too much in looking for it. So once you've got this, then what you can do is you realize you have a problem here because perhaps you have a plume that looks like this. And this would be the lowest concentrations, highest concentrations. More difficult, right, if it's a pulse-like plume. So if someone's injected something and gone away, this happens to be a continuous discharge, and so it would develop this shape. If it was sudden discharge, it would just be a bunch of centers progressively moving downstream, like in Borden, where it's more difficult to define. So then you go in and you take the site, you divide this plan view into an aquifer of some thickness into the page, and you mesh it out into a whole bunch of nodes which are joined by individual elements. So nodes with intervening elements. Simplest elements are triangles, could be quadrilaterals. And then you try and make a numerical model that takes this and tries to solve the equations for groundwater flow. And so what you do is you take the model, you put some boundary conditions on it by defining maybe the heads upstream, the heads downstream, and then trying to predict from the model with a given hydraulic conductivity or permeability what the distribution of head would be along this. So you have measurements of head. You can run the model to get predictions of head. When the measurements meet your predictions, then you think you might have a viable model. Once you have this flow field, then you can take the flow field to solve for, I guess you already solved for the head as a function of location in plan view. And if you have the head with location, you also have dH dx with location. And if you have this, you can calculate V Darcy velocity. I always want to say VD. And if you have Darcy velocity, you can calculate advector velocity. And then if you have advector velocity, you have enough to be able to put together the equations that describe behavior. And so then you can set it up, and now with the results that are computed from using this grid, I guess this would be matching the contours of groundwater flow in this particular case. This would be the section through them. This would be what would give you this plot that we just had here. And now you can merrily run the model to say, what if? What if our source is coming from here, and we suck a whole bunch of water out from here at some flow rate through a well field, and remove both the plume, which is present here, which we kind of drew up here, if the plume is here. And not only if we remove the plume, we keep on removing the plume, we'd stop anything going past this well field and getting further downstream, and we'll capture everything that comes down here. And what flow rate do we have to pump at to do that? And where should the wells be to capture it? Absolutely. And so those are the kind of questions that you might be asked to solve. So this would be just the equipotentials. So this means that water would be flowing perpendicular to these. This would be the Darcy velocity and also the advective velocity. And it doesn't really matter so much, but if you pump water out, this means that if it's coming in perpendicular to the contours on this side, perpendicular to contours on this side, it's not going anywhere. It's getting into a gravity well, basically, or a real well, actually, if you do that. So that's kind of the idea. And so you can look to see what happens here. I didn't really look to see what these are. These now, so these, pardon me, these are contours of equipotentials. So the water table, you can imagine this is the elevation of the water table as it goes down gradient. And this is the lowest part here, cone of depression. Highest part here, influent flow. But now, if you know what these are, you could also add these as advective fluxes. So you could think about, in the simplest way, releasing particles of contaminant and see where it gets carried downstream in a given time. And those are the simplest explanations of this kind of process that we can look at. So if you have the flow field, then that allows you to define the velocities. So you could release lots of particles at this site virtually in a computer code, and they'd get carried downstream, and you could contour their concentrations to be able to say what the plume would look like. And you can try, as I mentioned, lots of what-ifs. What if you put some wells here to be able to change the groundwater contours? And if you pump for a certain amount of time, and pump for even longer, whether this plume actually shrinks, how long it takes to shrink, etc. So that's really the task, to be able to make engineering predictions about what you have to do for a certain result. What you want to do is how many wells, how much flow rate with a given aquifer configuration and permeability, and how long would it take to be able to remediate this plume as a result of that. And so that's kind of where we're going with this. We used to run a problem with a code out of Fedder's book, but it's not in Fedder's book, and regardless, you don't have Fedder's book anymore. So we don't do that anymore. So there's 9 assignments, but there's only 8 that you have to do. So I am going to add something here. Add page. Right, so mathematical models. So this is the idea. So you'll remember that we have flow equation, and you know that it's rate of change with time of density times volume. This will give you new nightmares. This is fluids, which you don't need here because you've already done it and passed with flying colors. Equals 0. So you'll remember this, that this is dt rho v plus m dot equals 0. And so if, in other words, if you have a little cube, do this sometimes in that class. I don't know whether we did for you or whether you were indeed there that day. No, I do care, but I pretend I don't. Which would be mass in, mass out. So we do this. What have we done here? We've put in velocity is equal to permeability over viscosity 1 over porosity, d change in head with location. If we substitute that, then this middle equation goes to the groundwater flow equation, which you've seen twice now, which is at least twice, in Rachel Houseco's course as well. I just write it as simply as I can, not with the other dimensions added. And so this is specific storage, this is hydraulic conductivity. This is Darcy velocity, by the way. And this is Darcy velocity. So, flow equation. Transport equation, I won't go through the same. Advection dispersion equation would be, we've seen it many times. In its full form, it's the retardation coefficient times concentration change with time. Very similar to this part. Equals dl d2c dx squared plus transverse dispersion d2c dy squared minus advective velocity times rate of change of concentration in the x direction. Yeah. And so this is for our site, this is for x, this is for y. Oh, I should do this. I found out how to do this. So this is transverse, this is longitudinal. And so this is the geometry for this. So those are the two behaviors that we want to emulate. Flow behavior we talked about putting pumping wells in, making a groundwater depression, a cone of depression that takes the water out, but we want to use that to be able to find out the flow field because the transport field is superimposed. The advective transport field is superimposed on that flow field. So what we need to do is solve for the flow field first, and then on top of that, we can use the velocities in the x and y direction to be able to calculate for this behavior here. And I guess this is organized in the x direction, so there's only one principal velocity, which is going down in the x direction. So that's what we want to be able to solve. So just to make the point that fluid mechanics has some utility in this. It's kind of, I know we always think, me in the past tense, and you always think that these courses are relevant, but fluids and thermo are the first ones where you get partly towards your major. So what we're going to do, we're going to look at behavior of flow down stream, again using kind of an idealized core with a head drop along the length of that core. This is head. As we go from upstream to downstream, we're going to go 2, 3. And this is going to be, x, 3 meters, an actual example. And this would be the head at node upstream, I'll call it, fine. Upstream, and the head at downstream. And we have flow along this pathway. This is the velocity, not that it matters, I think, in this case. And we choose a porosity of 10%. And so if we go back to that picture of New Jersey, this would be the upstream part off to the far right. This would be the downstream part where you're sucking it out of the ground, all kind of reduced to a one-dimensional profile just to make our lives a bit more straightforward. And so what we could do is we could look at dividing this up in some way into a template. And so the template might be that we look at if we know H0, how did I number them? And this will seem strange, but it'll make sense later. So we'd like to be able to calculate that we certainly know this head, and we certainly know this head here as well, because we know we're measuring it upstream and we're measuring it downstream, and we have those values. So we have some boundary conditions, upstream and downstream. So what we don't know is what the heads are between those, and this would be the cross sections that we measure in the field, but we can also want to calculate in digital form to be able to figure out whether we're matching the permeabilities or not. So what we can do is make a model that represents that behavior. And so what we'll attempt to do is that on that grid that we had before, we had a grid of triangles, and at each of these triangular locations we'd have a value of the head defined just like we do here. Upstream we'd know it, downstream we'd know it, at the other points we don't know it. We could also make a grid that instead of being triangles was a bit more regular. Same situation though. We can create the grid that has these. Upstream we perhaps know them, the boundary conditions. Downstream we perhaps know them. But in between that, maybe we don't, and we have to solve for it. And so the reason for drawing this is that you could imagine that if we knew this one and didn't know this one, this one, this one, and this one, we could try and solve for it if we knew a big system of equations. So you could think about dividing this up into just including the ones that are the nearest neighbors. That's pretty good. So it only includes those ones which are, actually it doesn't include this one, but you get the idea. And so you can make from this a template, and that template would have, in this case, these nodes on this cross. HU we'd know, and these other ones we didn't know. And so this is the same idea as this. This is our one-dimensional template, which ultimately we'll use to be a two-dimensional template and a three-dimensional template. We won't do that, but we'll make the case. So the idea is this, that we can represent this system between these points. And if I draw a graph like this, and I divide it into two parts. This is x, this is h, so this value here. And for example, the change in head as we go across this could look like this and this. This would be delta x. And these magnitudes would be equal to the heads, and I'm going to go, so this is representing along this section along here. So this would be H3, no. How did yes. H3, H0, and H1. And so here we can do delta H, delta X. And so if we wanted to calculate, for example, we know that in this expression we have terms like this, and we can convert that term to look something like the rate of change in the x direction of the gradient of head. Right? This says how much does the gradient of head of this value change as it goes downstream. So we need to be able to calculate this, and then we need to first. And if we can do that, then we need to be able to calculate this. So the first part, and I'm just making some more space. Apparently I can't. I can. Sorry about that. Is that if we want to calculate what each of these two components are, we could calculate that the if I get it, that if we calculate this, what did I call it? I call this 1, and I call this 3, just because they're closest to H1 and H3. So if we calculate dH dx for one circle is equal to H1 minus H0 over delta x. Convention is yours to take the down one in the positive, x direction's further away, and subtract it from the one that's closest. This, in this particular case, is a negative gradient, etc. You could also, and that would represent the gradient at this particular point. Just happens it's the same over that whole interval, but we're making it represent this individual point. We can also calculate the head gradient at point over the section 3 in the x direction, which is equal to downstream minus upstream, which is H0 minus H3, again divided by the spacing between them. And so that gives us this part for those two locations. But the meaning of this term here is this is the difference in dH dx, which we've calculated at each of these 2 points. So this this is actually on this gradient is here, right? It's on this thing here. And this other one is on here. So these are the two magnitudes of these first order partial derivatives, dH dx, at these 2 points. And the definition of the rate of change of those is the magnitudes of each of these values and how they change between this point and this point. So this magnitude here would be this number, and this magnitude here would be this number. And so d dx dH dx is just equal to the rate of change between those 2 points of the one that's downstream, which would be dH1 dx, which is this, minus dH3 dx, which is here. So the values of these slopes at these 2 points and how they change over this length. This length is equal to delta x because it's in the middle of these divisions. And so if we substitute these values in here, then this would be equal to H1 minus H0 minus H0 minus H3 both divided by delta x and divided through by this delta x here. This is just dx. No, I can't use that. Delta x. I can't write times x squared, right? So one comes from these two, and one comes from this one. And so if you work that out, then gather terms, you end up with this d2h dx squared, which is what we're after. is going to equal h1 minus h3 minus 2h0 over delta over the length dimension squared. Units match up, right? The units of head are here. The units of the differential is x to the power 2, so this is x squared. So it's length over length squared. And if we assume that everywhere in the mesh that we're making, delta x is constant, and if we assume steady state means there's no change in time. So if this is equal to 0, then this is just the only term, and we'd be left with permeability times this, but it's equal to 0, so it doesn't matter because all these, it just matters what this term is. We could ignore permeability. So we could write, I guess, permeability on here, but we could also write that this is equal to 0. So if delta x is always constant, every spacing along here is the same, then this drops out. If the permeability, hydraulic conductivity along the length is just the same as well, then we're just left with 3 terms. And so so delta x equals constant, and also hydraulic conductivity is constant. And then the final expression is just going to be that h0 is equal to h1 plus h3 over 2. So if we go back to our little template as we had before, we have h0, h3, h1. All it's saying is if you have a magnitude of the head here, if you add these two together and divide by 2, taking the average, then this could be the magnitude of the interior magnitude. And because you don't know any of these values before you start, it will evolve, so you have to iterate through it to be able to get there. But it's a technique that's called relaxation. From the 1940s, before digital computers, when people were using slide rules and tables. So in other words, if you have a grid which represents this, all you have to do is work through the grid, adding the 2 heads on either side, dividing by 2, and replacing it with the intermediate one. You can do exactly the same calculation, so this is in 1D. You can do exactly the same calculation in 2D with a grid over, like the New Jersey site we had, but not triangles, but a rectangular grid. So it'd be H0, this is H1, H2, H3, H4, and H0 would be equal to the sum of all the terms, the averages of them, H1 plus H2 plus H3 plus H4, not surprisingly, divided by 4. So this would be 2D, and you could probably guess by inference what it would look like in 3D. So this would be X, Y, and Z. Again, this little template. And so this would be 1, 2, 3, 4. This would be 0, and this would be 5 and 6. And it would just be equal to, the center one is equal to H1 plus H2, etc., plus H5 and 6, divided by 6. Very simple. So all we're doing is taking these equations, making them into finite derivatives, and then using finite differences to be able to compute it. And the method by which we kind of advance towards a solution is called relaxation, because you just successively reduce the errors, and this guessed value for the inner head slowly asymptotes towards the magnitude. So this is a fun class. I like this. So we'll do an example. So let's have the example, which starts off with values here, h upper, and I'm calling this h1, h2, h3. No, this is down, right? This should be down. And so we know that this magnitude, to put a number, let's assume this h is equal to 1, this h is equal to 0. So if we do that, then on this magnitude would be 1, this magnitude would be 0, and we don't know what these are. So let's transfer it down here just because it's easy. So h upper, h1, h2, h downstream. And so we started off with this is equal to 1, this equal to 0, and the others we don't know. Let's, instead of saying we don't know, we make them equal to 1, because we can. Just a guess. We'd probably expect that this is the upstream high value and the downstream low value, that all the numbers should be probably between these. You can't have energy from this make a big head here, perhaps. So choosing numbers between these, and of course either 0 or 1 or anything between them would work in this particular case. So if now we go from upstream to downstream. So remember, we're going to take this template and we're going to add this one and this one, divide by 2, and substitute for this one. So 1 plus 1 is 2, divided by 2 is 1. So now there are only 2. So now the next one is we do this. So now we take this one plus this one, add them together and divide by 2. So that would be 0. We could use this one, but we might use better the one we've already calculated because it's already updated. So it wouldn't make any difference in this particular case. So it would be 0 plus 1 divided by 2, which would be a half. So we could do it again. Someone's rebooting. So we want to be able to go back onto this one. So we add upstream, which is always going to stay the same. So these will always stay. These are boundary conditions. They don't change. And so now, as we're moving downstream, we take 1 plus a half, which is 3 over 2, divided by 2, which is 3 over 4. I think. Yep. And now we move on to this one. So we'll take this, because it's updated, and this. So 3/4 plus 0 is 3/4. Divide by 2 is 3/8. So this would be 3/8. And again, it gets a bit boring after a while. Well, it doesn't get boring, it's kind of exciting. So again, 1 plus 3/8 is 8, 9, 10, 11/8. So half of that would be 11/16. Then 11/16 plus 0 would be 11/16. Half of that would be 11/32. Yeah, fine. And so you're iterating towards a solution. This upstream would still be 1, downstream would still be 0. And so if it's uniform permeability, you know from Darcy's law that V is equal to K over mu, no, sorry, hydraulic conductivity. Hydraulic conductivity dH dx. You know that the velocity here is the same as the velocity here, which is the same as the velocity here. So this is constant. Permeability, hydraulic conductivity is constant, so that by inference the gradient has to be constant. So all these gradients have to be the same. And so if that's the case, you could infer, or you could imagine that these intermediate heads would be 1, 2/3, 1/3, 0. And so these should be asymptoting to that. So this ultimately should be 2/3 and 1/3. And pretty close. After just this number of iterations, we're quite close to that. And so we're just working our way along. There's no reason in the madness. You could go down one way and then back the other way, right? We've chosen to go down and down and down. You could also go up, down, etc. You should end up at the right location. If you have a two-dimensional mesh, you have to do the same thing. You just work along it, then up it, and back and forth. Again, just calculating what the magnitude is of this internal node inside this star cross template, I guess. And if it's a three-dimensional problem, you just go along and across and up and down at the same time. That's it. So that gets us the ability to be able to solve this equation very straightforwardly. There are much more sophisticated ways to do it, but now we have a velocity field. So if we look now at the flow field, a transport field rather, then what are we going to do? Yeah, I guess. So we know that now we have this behavior along here. Upstream, node 1, node 2, downstream. Or actually, not really heads, but node 1 and node 2. And so now, for transport, we need to know, as part of our equation, the easiest thing for us to do is to realize that this is an important part, which is now not a second-order PDE, but a first-order PDE. So what we could do is we could write it out as advective velocity times dc dx, which is the term that we want to define. Or we could just think of it more usefully as advective velocity is equal to Darcy velocity divided by porosity. Darcy velocity is equal to hydraulic conductivity times dH dx. And from this solution up here, we know from this that the gradient for something that is delta x long is equal to 1/3, right? In each of these portions, this is going down by 1/3 over delta x, 1/3 vertically, and this is delta x because of our template description. And this is 3 meters, and so we could calculate exactly what that would be. So I don't know what I used. So if we put some numbers into this, hydraulic conductivity is equal to 1 meter a second. Ridiculous number, but easy. Porosity is equal to 0.1, 10%. dH is equal to 1/3. It's in meters, so it'll be 1/3 of a meter. And delta x would be equal to, these could also be deltas. This is equal to 1 meter. And so if you calculate the advective velocity is equal to hydraulic conductivity over porosity dH dx, and substitute those numbers. My writing is getting really very neat. 1 meter a second. If you won't talk to me, at least I can talk to myself. 1/3 of a meter. Porosity is 10%. And times 1 meter. And if you do that, it turns out to be, this would end up being 10 on the top, divided by 3. Is that right? Yeah, 10/3 meters a second. And that's the advective velocity. And so I guess always have to write these out, not smart enough to remember. Length is equal, velocity is equal to length over time. So length is equal to velocity times time. So if we choose an know an advective velocity, we multiply it by a time step, then we know how far we'd go. So what we can then calculate is that x, yeah, right. So x is equal to x0 plus delta x. So you start off with a particle. So what we're going to do is we're going to release a particle here, particle of contaminant, and it's going to track downstream. We know the advective velocity that's carrying it downstream because we know the gradient of head and the hydraulic conductivity and the porosity. So that gives us an advective velocity. So we know the velocity it's moving downstream. So in a given length of time, we can calculate how far it goes and just mentally move that particle of contaminant down however far it goes. If we put a cage around it and calculate how many of those particles are in that cage, we can calculate kind of a proxy concentration. And so that's what we're doing here. So this is the location of that particle at some time, which will be where it was initially, plus how far it's gone downstream. And how far it's gone downstream will be x0 plus delta x. Delta x is L, which is velocity times time. No juice?
No.
Okay, I shouldn't have asked. So the idea is simple. So you start off with the location where you are, which is this. You have in a time step, you go a certain length, you add that length to where you were, and you find you move your particle to a new location. And so you can just release a whole bunch of particles which have a specific small amount of mass, allow them to migrate downstream, and that will give you a location of how far the front is going. So I guess the front would look like, if you count how many of those particles you have per unit length along the front, then you'd have a distribution like this. This area would just be the plume. Concentration would be C over C0 equals 1, C over C0 equals 0. So we're just utilizing the fact that we can calculate what the flow field is to solve this equation. We use finite differences to do that. It's really very simple. It comes down to just averaging the magnitudes of heads surrounding you and substituting that average for the central one, working through the whole grid to do that. That gives you a distribution of hydraulic gradients. You can use that distribution of hydraulic gradients here in one-dimensional to calculate an advective velocity. If you know the advective velocity, you can, for a given time step, you can calculate where those particles go. And so the only other relevance of this in the other things that we've done is the Peclet number is known as an advective velocity times a length divided by a dispersion coefficient, dispersion amount, longitudinal dispersion. And we also defined a Courant number, which is we also called a pore volume. When one pore volume is filled, all the water is being renewed within the core, and it's at the discharge point, which is equal to advective velocity times time, or time step, divided by dispersion. No, delta x, not dispersion. And these happen to be useful here. One is that this first order derivative that's present here is actually pretty tough to solve for because it's kind of unstable. This is a really easy equation to solve. This is not so easy to solve because it's a front that's kind of propagating downstream. This is kind of a diffused, smoothed out area which is really easy to solve. This is a front that's moving downstream and has a shock front, a sharp front to it. So it's not very easy to solve. So instead of doing it by finite differences, it's just done by what's called, this is called particle tracking, for obvious reasons. But this finite difference solving of this flow equation is almost always stable. You always get a solution, and it's usually a good solution. This solution, because of this sharp front, is really dependent on your choice of time step and on the fineness of your grid. To get a really good solution, you have to have a really fine grid, lots of these points, and you have to have a small time step to capture these particles moving forward. And both of those attributes are kind of captured in these two numbers. So this works best if the Peclet number of the system is less than 3 to 5. And so you want this number to be less than 3 to 5. You have no control in your system on the advective velocity because that's the physical system and it's going at that velocity. You don't yet have you don't either have a control on the dispersion coefficient because this is a function of, for mechanical dispersion, on the flow velocity and the length of the plume divided by 10. So the only parameter that you can control is this. So to get a Peclet number that satisfies this, you have to make a mesh that instead of looking like this, looks like this. So this will take a Peclet number of 10, I don't know, and reduce it to a Peclet number of 2.5, because I had about 4 of these things in each division. So you can't control the velocity, you can't control dispersion, but you control it by making a really fine mesh, and then you potentially get a good solution. The other constraint is that if you have a known advective velocity and a known length, so delta x here isn't the length of the core, but it's the distance between these points. So this would be delta x. And so you could imagine that if you have a particle that's steaming down here at high velocity, then if you have, by trying to limit your Peclet number, made lots of small divisions, then that particle can go upstream and go right the way across an element and go downstream without ever registering in the next element. And so what the Peclet number means is that the velocity times time is the length of one element. And so what this is saying, the Courant number should always be less than 1. A Courant number of 1 means it goes from upstream to the downstream boundary in exactly one time step of delta t. If the time t step is less than that, then it doesn't get to the outside boundary, and therefore it gets accounted for in this bin, so you can draw the cloud as it moves downstream. If delta t is too big, then the particle goes from here. It might go out of the system before you register it. And so these two physical parameters are actually useful in judging how you can get a mesh that works. If it doesn't work and gives you bad ideas, bad results, make it finer by putting in more elements. And of course, if you double the number of elements in a one-dimensional grid, you double the size of the matrix that you're solving. If you double them in a two-dimensional grid, then you quadruple them, multiply them by a factor of 4. And if it's in a three-dimensional grid, I guess it's to the power cubed, so it's 8. So if you double them 4 times. From going from a one-dimensional grid and doubling the grid spacing, you'll double the computational size of the number of equations. If it's a two-dimensional grid, you'll multiply it by 4 times, and if it's a three-dimensional grid, you'll multiply it by 8 times. So there's a cost that comes with making the grid finer, because it means it'll take longer to solve your problem. Perhaps longer perhaps outside the memory of your system as well. And also, even if you do have a fine enough grid to perhaps give a good result, if the time step is too big, which you'd like to use a big time step so you get to the end of 30 years, which is your lifetime of the project, that if delta t is too small, it just has to go through too many iterations to get there, and so it has a problem. That's it. My favorite class. You and this topic. All right, that's it. I don't have a punchline for you. So if you end up working in this area, you'll work in an office, no doubt you'd use computer programs to do these things. You almost certainly never have to know how the inner workings of those work, but knowing the mechanisms by which it does it, it's really very simple for these two. Solve the flow field, get the distribution of velocities, and then with those velocities, solve for the random walk motion of those contaminants downstream, and then come up with snapshots of what the plume looks like at time A, times B, times C, and then change it around to be able to remediate it by sucking that water out of it and doing it that way. Okay. Thank you. Questions?